All right, we're going to ease our way into the chapter on exponentials by doing a little bit of review of the rules, because everything that we're going to learn about exponentials is going to kind of reverse a lot of these rules. So just a reminder of the rules, we have the multiplication rule, and that is that if we have x to the a times x to the b, we get x to the a plus b. So you can think of this if I have like x squared times x to the 5. This is the same as xx times x, right? Just multiply x by itself 5 times. And then if you count, there's 7 of them. There's 2 plus 5 of them. 5, 6, 7 equals x to the 7. Right, so that one should kind of make sense. If we look at the next one, the division rule, so x to the a divided by x to the b, then we get subtraction. So let's say we have like x to the, let's say x to the 5 divided by x to the 2, right? So this would be xxx over 2 x's. And then what you get is that little bit of cancellation here. 2 of them will be sort of removed from the top by doing this, and that's why we get 5 minus 2 left over. So x to the 5 minus 2 is x cubed. And then finally, the power rule. So let's say we have, let's stick with our 5s and 2s here, x5 to the 2. So what we've got here, this is the same thing as, well, that's x5 squared, which is the same thing multiplied by itself. And what you can see is there's 2 groups of 5. There's 2 times 5 of these. And so we get, I'm not going to write them all out. You can see there's 10. But that's the idea. That's where the 5 times 2 is coming from, and that's the logic behind all of these. So just a little bit of simplification work. We can do these by either one go type multiplication, or we can do it in several steps. So I'll just do these in several steps to highlight the rules. This one we can simplify across the top. So that'll be y to the 3 plus 7 divided by y squared. So y to the 10 over y squared, right? Because that's my multiplication rule. And then what we've got is the division rule. So that's going to be y to the 10 minus 2 equals y to the 8. So we can get these answers without writing out a whole bunch of y's, fortunately. For part B, I didn't really actually touch on this, so I suppose I can write a different rule over here. So here, if we've got xy to the a, you get what's actually sort of like a distribution of the power. And so what you get is actually x to the a times y to the a. So it sort of distributes, and so I'm going to do that with that 4 here. So what I can do is just push the 4 sort of the way that multiplication distributes through addition. It's very similar. And so what I'm going to get here is 2 to the 4, x squared to the 4, and y cubed to the 4. And then as we work across, we have some different situations. 2 to the 4 is 2 times 2 times 2 times 2, so that's 16. X times 2, x squared to the 4. This is where now we use this power rule, the third rule up there. That's going to be the product of 2 and 4. And then the y, again, 3 to the 4. That's again a product. And so, yeah, we just simplify those products. I should get 16 x to the 8, y to the 12. So those are all of our basic kind of exponential simplification rules. I do want to touch on a couple more rules. All right, so I've cleaned this up a bit, and I've added a couple more rules on the right here. So specifically these 2 rules. These are not really algebraic rules just so much as they are actually notation rules. So they kind of are spawned from the rules before, but just to explain these ones, we have x to the negative a equals 1 over x to the a. And so the justification for that is that if I do x to the negative a times x to the a, then what I should have if I follow this addition rule on the left is I should have x to the negative a plus a, which is 0. And with the exception of x equals 0, that actually should be 1. Anything to the power of 0 equals 1. Maybe I'll actually go back and explain that one on the side too. That's actually probably worthwhile to talk about. Yeah, I will go back to do that. So yeah, anything to the 0 is actually equal to 1. So what that means is that since x to the negative a times x to the a equals 1, what we can write here is that if I just rearrange this equation, I would divide both sides by my x to the a, and that actually tells me x to the negative a equals 1 over x to the a. So that should solve that for you. In case you've forgotten about the, yeah, the x to the 0 equals 1. Yeah, it's kind of just something that's easier to know as a convention. I think the explanation, more than anything, actually just sort of comes from the fact that, like, if we wrote a table of values up across the top, let's say if I have x to, let's say I do 2 to the 1, right? That's 2. 2 squared is 4. 2 cubed is 8, etc. So if we go to the right, we can see each time we multiply by 2, and that's how we get this higher power. So it makes sense that if we are going to the left, right to left, that as we reduce each time, we would divide by 2. And so that's kind of where that convention comes from. But it's also really closely tied to this sort of negative exponent convention. They're all sort of come together like that. And so I'll do the one on the right as well. So this these roots and why these roots make sense to write them like this. So if I take x to the 1 over a, and if I raise that to the power of a, then, and I use my power rule for simplifying that, I get the product 1 over a times a, and that is actually just 1. 1 over a times a is a, so I get 1. So by definition, what we have is that x to the 1 over a is the thing that, when raised to the power a, we get x. Or you can think of it, we could actually just take the a-th root of both sides. Either way that we think about it, we're going to get, by definition, this x to the 1 over a is a root. So x to the 1 over a. So yeah, so we had this. This came directly from the equation above. Now if I take an a-th root, sorry, that was x on the right, not 1. So if I take an a-th root, by construction, the a-th root should cancel out with that a-th power, and it leaves us with this definition that we're given, x to the 1 over a equals a-th root of x. So that's why we write them in these different ways. So just a few things that we're going to be able to do with this, and we'll see little bits of this throughout this section. Yeah, so a couple more simplifications on the left here. First of all, we've got that -4, so I'm going to use the that distribution rule. Actually, you know what? I don't like that. I'm not going to start with that rule. What I'm going to do first instead is deal with the fact that I've got this minus. Yeah, I think what I'm going to do instead is actually just go ahead and use this rule. The negative a is 1 over x to the a. So that's going to allow me to actually flip this whole crazy fraction. So I'll get 3x cubed over z squared to the 4. And then I will be able to use that distribution rule here. So maybe let's do that in red. Yeah, so I can do that distribution. So this is going to distribute on all of the pieces, the 3 multiplicative pieces in that expression. I'm still going to have this big 1 over on the top. So I'm going to have 3 to the 4, x cubed to the 4, and z squared to the 4. And in doing the distribution, what's nice is that I've got this 1 over a fraction. That actually is going to allow me to flip the fraction. So z squared to the 4 over 3 to the 4, x cubed to the 4. And then now I should be able to do the power rule, which I've underlined in orange. So I'll just do it in orange here. So that'll be z to the 2 times 4 is z8. 3 to the 4 is the number 81. And x to the 3 times 4 will be x to the 12. And so that should be my final result there. There's a lot of ways that you could do this. You could have just taken the minus and used that to flip everything on the inside. So we could have sort of jumped sideways a little bit and said that this was equal to, so just taking that minus and turning into a positive 4 on the outside and flipping everything. And to be honest, that's probably an easier way to go about it, but I wanted you to see all these rules in action. And then you just push the 4 onto everything. There's lots of different ways we can approach these things. And finally, let's see, what color have I not used here? I guess I'll go with blue. So this one, we've got all these roots. A root without a number is basically a square root. So we've got that much. So I can use those rules. That square root is x to the half. And on the bottom, that'll be x to the third. You might notice I said assume that x is greater than 0. That way we don't have any weird domain problems, because we are dealing with roots, which sometimes have domain problems, and division, which sometimes has domain problems. This way we can just avoid all of that. So now I've got this written as rationals. That's going to allow us to do arithmetic on these, because now I get to apply my subtraction rule. Find a color. Let's do this one in this dirty brown color. So now I get to deal with division. It's just going to follow right along with that rule. What I'm going to have is x to the half minus x to the third. And if you know your fractions, that should be 3/6 minus 2/6 is 1/6. So we get x to the 1/6. And now if I actually revert the rational exponent rule, the blue one, we can see that's actually the 6th root of x. So that one actually cleans up quite nicely into a completely different root. So as far as these, we actually don't do a lot of what's going on in example A here. It'll come up every now and then, but it's not really the crux of this chapter. You will need to be able to do these rational conversions for some questions every now and then, and it's also really important for calculus to know this rule. That should be enough of a review to know all of the rules. Let's do a little bit more review, solving some really simple equations, and then that's it, hopefully.